Heat of vaporization is the amount of heat needed to vaporize 1 mole of liquid at its normal boiling point. So that's to take water from the liquid state to the gas state. That's an endothermic process. We need to put energy in. So delta H is a positive number. It's 40.7 kilojoules per mole, somewhat temperature dependent. Here's a table listing some heats of vaporization for various liquids. We see that for rubbing alcohol and acetone, which are more volatile than water, it requires less energy to vaporize those. When a substance condenses, it's the reverse process. Same amount of heat is involved, but now it's a negative number because heat is released instead of being absorbed. And this is a useful conversion factor to relate number of moles of substance and amount of heat involved in either vaporization or condensation. The number is the same, the sign is different depending on whether you're vaporizing or condensing. So let's do this problem. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So we're going to need the heat of vaporization, which is 40.7. So delta H vap is 40.7 kilojoules per mole. So we are vaporizing. Is this going to be a positive number or a negative number? You have to put heat into it to vaporize it? Yes. Yes, we do. So this is going to be a positive number. There's no equation for this. It's dimensional analysis. So we're given 2.58 kilograms of water, and we want the amount of heat in kilojoules. So we need to find a path that'll get us from kilograms of water to kilojoules of heat. Our heat of vaporization is our conversion factor. This relates kilojoules and moles. So this tells us that in the middle here, oh, that's not, maybe over here. In the middle here, we need moles, because this will allow us to convert from moles to kilojoules. We're given kilograms. So what we need to do is we need to convert that to grams and then convert the grams to moles. Now, exactly how you convert to grams is up to you. Some of you are very comfortable and adept at just doing that conversion in your head. Others are not. If you need to write it out, there's no shame in that. Write it out so that you get the correct answer. So I'm just going to follow the path that we wrote here. So 2.58 kilograms, and I'm going to have grams here, and then moles, and then kilojoules. And I'm going to put the units in so they cancel out. And then I'm going to stick the numbers in. Relationship between kilograms and grams. Kilo means 10 to the 3. The kilo's in the denominator, so I want to put the 10 to the 3 in the numerator. Grams to moles is the molar mass. 2 times the mass of hydrogen plus 1 times the mass of oxygen is the mass of 1 mole of water. And I just happen to remember that's 18.02. And then this guy over here, this is where the heat of vaporization comes in. So it's 40.7 kilojoules per 1 mole. And then we calculate 2.58 times 1EE3 divided by 18.02 times 40.7. My calculator says 5827.192, blah, 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 kilojoules. I look at all the numbers that I have here. I'm just multiplying and dividing. I've got 3 sig figs, 3 sig figs, 4. So this should be rounded to 3 sig figs. So probably the best answer is 5.83 times 10 to the third kilojoules. 5,830. Not the best, but acceptable. Any questions? If we have a relatively volatile liquid in a sealed container, we get a dynamic equilibrium that is established between that substance in the gas phase and the liquid phase. Because as molecules evaporate, they cannot escape from the container. So they evaporate into the gas state, but once they're there, they do what gas molecules do, traveling in a straight line until they collide with something, and eventually they will collide with the surface of the liquid again and get trapped. The rate of evaporation depends on a couple of things. It depends on the temperature of the liquid. If the liquid is warmer, there are more particles at higher velocities with higher kinetic energy that are able to escape, and so it will evaporate faster. If the surface area is larger, the rate of evaporation will be greater. But in this situation, both of those are constant. So the rate of evaporation is constant. The rate of condensation is going to depend on the concentration of gas molecules. We don't usually talk about concentration of gas molecules, we talk about the partial pressure. It's going to depend, though, on the number of gas molecules in the gas phase in this container, because more gas particles here means a faster rate of condensation. So we get this dynamic equilibrium established when the rate of evaporation is equal to the rate of condensation. Initially, there is only evaporation and no condensation because there's nothing up here to condense. As the concentration or the partial pressure grows, the rate of condensation increases, and at some point it will equal the rate of evaporation, and then we have a dynamic equilibrium. Here's looking at these rates in graphical form. Here we have the rate increasing on the y-axis as time goes on. The rate of evaporation stays the same because the temperature isn't changing, the surface area isn't changing. The rate of condensation starts out at 0, there's nothing to condense. As we get more and more gas particles in the above the liquid, the rate of condensation increases until we get to a point of dynamic equilibrium, and then it stays the same. So the partial pressure of the gas above the liquid is known as its vapor pressure. And that vapor pressure is going to depend on the temperature, and it's going to depend on the strength of the intermolecular forces. If those intermolecular forces, the forces holding the particles together, are weak, then we'll have a high vapor pressure because the rate of evaporation will be greater. And so we'll end up with this equilibrium coming together at a higher rate. Any questions about that? If we disturb an equilibrium, the system will respond to minimize that disturbance. So an equilibrium is like a person who doesn't like change. I'm not a big fan of change unless it's my idea. So there's a lot of things that change in my life that I'm not real happy about. And so I try to adjust things to make them more like they were, and that's what an equilibrium does. If we have this equilibrium of gas and liquid in a sealed container, and we increase the volume, that causes the pressure of this gas to decrease because there's a larger volume and the same number of particles. So the pressure goes down. What does that do to the rate of condensation? The rate of condensation depends on the pressure of that gas. If the pressure goes down, does the rate go down, stay the same, or increase? We've got particles moving around in here. If they're farther apart, if they have more room to roam up here, then the chances of them getting trapped again are less. So the rate of condensation goes down. Rate of condensation goes down. The rate of evaporation stays the same. So given a little bit of time, we will reestablish the same vapor pressure because the condensation will compensate. If we squeeze down this container and make it smaller, increasing the vapor pressure here, that's going to cause the rate of condensation to increase. More of those gas particles will get trapped in the liquid, and that will continue until, again, the rate of evaporation and condensation is equal, and we'll end up with the same pressure. So the system responds to reestablish equilibrium, and it's trying to do so to get it back to the original state as much as possible. Any questions? The vapor pressure, as I mentioned earlier, depends on the temperature of the liquid. Because as we heat up a liquid, increasing temperature reflects increasing average kinetic energy. And it's the higher kinetic energy molecules that are able to escape. If we increase the average kinetic energy, we have more of those higher energy particles that can escape. We increase the rate of evaporation. So for many substances, a small change in temperature gives us a large change in vapor pressure. This is a graph showing vapor pressure in torr versus temperature. Some things like ethylene glycol do not show much of a difference in their vapor pressure, but other things like diethyl ether, ethyl alcohol, water, if we go from 80 degrees to 100 degrees, we see a large change in the vapor pressure. When a substance boils, we've increased the temperature to the point where the vapor pressure equals the external pressure. Let's go back to this graph for a minute. At 100 degrees Celsius, the vapor pressure of water is 760 torr. That's atmospheric pressure. As we increase the temperature of water, the vapor pressure increases and increases, and when we get to 100 degrees Celsius, the vapor pressure equals atmospheric pressure. The particles on the inside of the liquid now have enough thermal energy to break away from their neighbors and form little pockets of gas. And those are the bubbles we observe when we see a liquid boiling. Gas molecules, or molecules in the gas state, have gathered together in little clumps, and then those are much less dense than the liquid, and they rise to the top. So the normal boiling point of a liquid is the temperature at which its vapor pressure is equal to 1 atmosphere. For water, that's 100 degrees Celsius. For other liquids, it's going to be a different temperature. This has implications for cooking at high altitudes. I don't know if you've ever noticed on like a cake mix box, too many X's, there'll be high altitude directions. The water will boil when the vapor pressure equals atmospheric pressure. What if you're in Denver and you're a mile above sea level? Atmospheric pressure is lower in Denver. So water boils at a lower temperature. Well, you have to account for that in your cooking. Once we get to that boiling point, adding more heat does not increase the temperature. It may increase the rate of boiling. The water may boil faster, we'll see more bubbles, but the temperature remains the same. And this is kind of an odd concept and one that a lot of people haven't really considered. If you're trying to make spaghetti, right, and you get a pot of water boiling. If if it just started boiling, or if it's been boiling for 5 minutes, the temperature of the water is the same. It doesn't matter. What happens in a place like Denver or high altitude, the water's going to boil at a lower temperature. So it's going to take longer to cook your food. So as we add heat, temperature increases until we get to the boiling point. We're still adding heat, but all of that heat is going into boiling the liquid. Because what's happening as it's boiling is it's the higher energy particles that are escaping, which tends to reduce the temperature of the remaining liquid. So all the heat that's being added goes into molecules escaping. The temperature won't go up until they're all in the gas state. Once that last bit of liquid has boiled, now the temperature will shoot up. As we saw in this previous graph, let's just go back there real quick, this guy, the relationship between vapor pressure and temperature is not linear. These are curves, not lines. But there is an equation that describes that relationship. It's an exponential relationship. The vapor pressure is equal to a constant beta. This is just a kind of a funky way the book uses. This is E raised to this power of the heat of vaporization over RT, and that's negative. So that's just not a very useful form. So if we rearrange it by taking the natural logarithm of both sides, we get the natural logarithm of the vapor pressure is equal to negative heat of vaporization over R times 1 over the temperature plus the natural log of beta, which is just a constant. This is in the form of a line. You're like, oh, that doesn't look like a line. Y equals mx plus b. So if we graph y, the natural log of the vapor pressure, versus 1 over the temperature as x, we get a straight line, and the slope is negative delta H over R. The intercept is the natural log of beta. That's really not a very useful constant, but the heat of vaporization is useful. So we can actually determine the heat of vaporization experimentally by measuring the vapor pressure at various temperatures. I don't know what substance this is, but they measured the vapor pressure in millimeters of mercury and took the natural log of that and graphed that on the y-axis versus 1 over temperature. Again, we need to use Kelvin for things like this. And so we get this line. You use a computer to get the best fit equation for the line. And we find that the slope of this line is minus 3478 Kelvin. That's equal to the negative heat of vaporization divided by R. The R that we're going to use here for unit's sake is the 8.314 joules per mole Kelvin. And so when we take the slope, negative slope, and we multiply by R, then we can calculate delta H, so 28.92 times 10 to the third joules per mole. Any questions? So this is for practice question. We're given the data here, the temperature and the vapor pressure in torr, and we're asked to determine the heat of vaporization of carbon tetrachloride. You have to do a graph to figure out what the line is. And every semester I think I need to do that and stick it in here, and time gets away from me and I don't. So I'm not going to actually solve this, but I'm just going to talk about how we would solve it. You would want to convert temperature to 1 over temperature. And so you take 255 Kelvin, 1 over 255 is 0.00392. And you would do that for each of these. This is something that's best done in a program like Excel, where you can type this equation in once and copy it, and it'll do all the calculations for you. And then for the vapor pressure, we want the natural log of the vapor pressure. So we want, where's that button on my calculator? There it is. The natural log of 11.3 is 2.425. So the natural log of the vapor pressure. And then we're going to make a graph of natural log of the vapor pressure versus 1 over T. You use Excel to find the slope and the intercept of that line. The slope is what we're interested in. The Clausius-Clapeyron equation tells us that the natural log of P is negative delta H over R times 1 over T plus the natural log of a constant. So this is the slope. From your graph, you determine the slope, and then delta H, heat of vaporization is going to equal negative slope times R, 8.314, blanking, joules per mole Kelvin. And that will allow you to find the heat of vaporization. Any questions? There's another form of the Clausius-Clapeyron equation. It's called the two-point form. And we just did some math on this, basically. This early in the morning, I don't know if any of us are really interested in how they got this, but this allows us to compare just 2 points instead of having to do a graph and find a slope. So if we know the heat of vaporization, and we know the pressure at one temperature, then we can find the pressure at another temperature. Or if you know the pressure at 2 temperatures, then you could use also this to calculate the heat of vaporization. Let's do an example of this. Propane has a normal boiling point of minus 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure of propane at 25 degrees Celsius? Well, we need this 2-point form. The thing I have a hard time remembering is the 2's and the 1's. 1 over T2 minus 1 over T1, it's P2 over P1. So let's see if I can write that down. The natural log of P2 over P1 equals negative delta heat of vaporization over R times 1 over T2 minus 1 over T1. The temperatures have to be in Celsius. So we want the vapor pressure at 25 degrees. So let's call that P2, just because I think it's going to be easier to solve for P2 instead of P1. So we're going to call this P2, and that's going to equal 298 Kelvin. I'm sorry, that's not P2, that's temperature 2. That's the temperature, duh. So then this is what we're going to call T1. T1 is minus 42, so we have to take minus 42 and add 273. So that's going to equal 231 Kelvin. And they gave us delta H. What is the vapor pressure at minus 42? They didn't give us a pressure, did they? They're asking us for one pressure, but they didn't give us the other one. This is the boiling point. At the normal boiling point, what's the vapor pressure? Yeah, 760 millimeters of mercury or 1 atmosphere. So this is going to be 1 atmosphere or 760 torr. Now here's a question. Does the unit on the pressure matter? Does it have to agree with R? What happens to these two pressures? The units are going to cancel out. The units here, we've got one pressure divided by the other, so the units are going to cancel out. So we can use torr or atmospheres. The question doesn't specify, so let's use atmospheres. Makes the math easier because then one of the pressures is 1. So this is one of the few equations where it's not necessarily better to rearrange the equation first, because you've got natural logarithms in there and you've got fractions being subtracted, and it's kind of a mess. So let's put in the numbers and then see what we can do to simplify things. We're looking for P2. P1 is 1 atmosphere. And delta heat of vaporization, we've got our heat of vaporization is not 40. What? Oh, it's just one of those days. So the heat of vaporization is 19.04 kilojoules per mole. R is 8.314 joules per mole Kelvin. 1 over T2, T2 is 298 Kelvin. T1 is 231 Kelvin.
Am I supposed to convert the kilojoules into joules?
Yeah, we do have to be concerned with the kilojoules to joules. So I wrote all this out just using the units provided, and then we look at the units. We can subtract these, they're both in Kelvin. Here we have joules, there we've got kilojoules. So we do need to take care of that. So what I'm going to do is I'm going to get rid of kilo, and I'm going to put what it means instead. And that'll take care of that. So now all my units are going to work out on the right side. And so I'm going to do this messy math on the right side of the equal sign. Negative 19.04 EE3 divided by 8.314 times the quantity 1 over 298 minus 1 over 231, close parentheses, equals. And so this equals 2.22. This is one of those situations where we've got a mess with significant figures. So I'm just going to write down 4 of them here. What are the units on that 2.229? Are there any units? The joules canceled out. The moles canceled out. These kelvins don't look like they're canceling out, but what I've got here is 1 over T times 1 over T with the kelvins here, and so the kelvins actually cancel out too. That quantity there is unitless. So I have the natural log of P2, and the unit there, I guess, would be per atmosphere, is equal to 2.229. How do I find out what P2 is? We need to do the opposite function of natural log, which is e to the x. So this means that P2 it's not to the minus, it's just atmospheres. Sorry. P2 equals E to the 2.229. And the unit will be atmospheres. So pressure 2 is 9.291 atmospheres. Now, that seems like kind of a high pressure, and it is. But propane boils at minus 42 Celsius, which is very, very cold. At room temperature, then, we would expect that the vapor pressure would be pretty high, and it is. Any questions? Well, we've talked about gases and liquids, and we're talking about vaporizing things. What if we have a sealed container with a liquid in it? The liquid's going to vaporize and establish an equilibrium. And then what if we heat that in the sealed container? What's going to happen? Well, as the temperature goes up, the pressure's going to go up, because the rate of evaporation depends on the temperature of the liquid. So if we heat it up, the vapor pressure will increase. This is a sealed container. So as the vapor pressure increases, the gas becomes more dense, the liquid becomes less dense, and at some point, the gas and liquid states are going to merge. And it will be neither gas nor liquid. It will be gas and liquid at the same time, and that's called a supercritical fluid. So here is peering into a window of a sealed chamber where this is occurring. Here's the liquid and the gas. As we heat it and it's sealed, the pressure increases, and at some point the meniscus disappears. The boundary between gas and liquid disappears. That's called a supercritical fluid. The temperature at which that occurs is called the critical temperature. Above the critical temperature for a substance, the liquid cannot exist. The pressure at that transition is called the supercritical pressure. Supercritical fluids are actually very useful as solvents. When they decaffeinate coffee, they use supercritical CO2 to to remove the caffeine without removing all of the stuff that makes the coffee taste good. It also doesn't leave any harmful residues behind. There are other things that you can extract caffeine